Today, my talk has one main thesis. And the thesis is that consciousness, and by that I mean subjective experience, such as your visual, perceptual experience, is a natural phenomenon. It can be mathematically described just like the rest of the physical world, and hence it can be studied by the natural sciences. And that's important, that mathematical part is important, because some people believe, very smart people I should add, that this is all we can do. So I put two quotes here. The first one is that the essential fact is that all pictures, meaning ideas or descriptions, which science draws of nature, and which alone seem capable of according with observational facts, are mathematical pictures. That's a little bit of a mouthful. I think Stephen Hawking put it more eloquently by saying, all one can do is find which mathematical models describe the universe we live in. So it seems that the end goal of science, in a way, is mathematics, or it's the best we can do in science. And so I want to make this case that we might be approaching this point when it comes to consciousness, such as visual perception. So first, what I'd have to do is I'd have to define a little bit what I mean by consciousness. In particular, I want to make clear that I don't talk about some of the things that if you Google consciousness and you end up at some yoga retreats, things like that is not what I mean. At the same time, I also will define consciousness differently than it might be done in a lot of cognitive psychology today, where it's equated with working memory or a combination of other cognitive functions. I'm not talking about function. I'm talking about being, about the fact that you are conscious. Then I will talk a little bit about why that's a problem for science and the struggle that science has with consciousness, or had with consciousness. I would then keep in that historical lineage and show that very early on, actually, people realized that there's a flaw in science's aversion to consciousness and that it can be mathematically described. Then I will show you a little bit about the neuroscience of consciousness, which has happened over the last couple of decades and which I happen to be very lucky, together with some people, be a little bit of a part of, and where we made inroads into understanding the brain mechanisms of consciousness. And I will show you how that did get stuck in a way a little bit. We did great inroads, but then there was a question, how do we move forward? And show you that in the last 5-ish or more years or so, there's been a massive leap forward. And that is what I would call the mathematical turn. OK, so what do I mean by consciousness? So typically, what we're being told in neuroscience classes, especially when it comes to vision and visual perception, which I just said, a subjective experience is a big part of your consciousness, it's very straightforward. There's photons out in the world. Often we don't even think about that there's physics involved, that there's photons. There's images, right? And so these images land in the back of your eye. There's a projection, this two-dimensional photograph almost. And then we will tell you what we've learned about how that gets translated into action potentials, into neural activity, and it moves throughout the brain. And then we will tell you it doesn't just move forward. There's also this activity that comes back, this feedback activity. And hence, you got perception. Now, of course, people have realized there's a problem here. We're just talking about atoms moving ping pong balls in a void. And no matter how much we try explaining to you what all of these neurons do and these action potentials, it's not obvious how that leads to you seeing color in an image. And there's, of course, more problems with that approach. So here's a nice demonstration that I'm borrowing from my colleague, Michael Cohen. I believe what you're seeing here is a graduate student lounge at Harvard. And you can get a nice conscious perception of what's all in this graduate student lounge as I'm keeping talking. And so you have this idea that, yes, there's stuff out there in the world, and I'm perceiving it, so my conscious perception. But of course, all of this, I just said, it's a demonstration, it's just an illusion. So while I was talking, a lot of things changed. This was what we ended up with. This is what we started out with. Who saw these changes? All of them? Most people don't. And so that shows you that there's what we call naive idea, naive realism, that your perception is really close to the world doesn't hold. So there seems to be more going on in what eventually leads to your perception. There's more that we'll have to explain. Now, the other question is, when it relates to these cognitive functions, would you rather lose your consciousness or your memory? Well, I don't know about you, but there are examples from the literature, empirical examples we can draw from. So you might have heard from patient HM, who had a lesion in his amygdala and entorhinal cortex and lost a lot of memory. Not all of it, there was still working memory, but lost a lot of memory. And so you could walk into a room, get introduced to patient HM, leave the room, come back, and it would start all over again. It would be like in the movie Memento. So HM was living in the here and now, in the present. That's an actual photograph since HM passed away, so there's no more privacy restrictions. And he looks pretty happy to me. So if you have consciousness but no memory, it seems that's happy. And if you have memory maybe but no consciousness, it looks like you're not that happy. So of course, most people would say, if you can take away one of these things, consciousness or memory, don't anesthetize me, don't put me in coma or brain death. I'd rather keep my consciousness than my memory. But when it comes to understanding what the brain mechanisms are for memory or consciousness, there's this big gap. So I just went on PubMed, and I looked at the neuroscience of memory. And you can see that since 1998, where there were 262 papers on that, now we have overall, in all the decades, we have more than 55,000 publications on the neuroscience of memory. If we look at the neuroscience of consciousness, it's very meager. So I took the same starting points. I found 232 results. So what you actually have to do, you have to squish it, and you see how little papers there are on the neuroscience of consciousness compared to the neuroscience of memory. So why is that? And so the next thing I will do is argue that's because of how science started and some ground rules that were laid at that time when science started. So when did science start? Well, it's a little bit like asking when, if you grow a beard, does a beard turn into a beard? There doesn't seem to be a discrete point where we can say, oh, it's a beard. Before that wasn't. And the same is true with science. So obviously, we know that thousands of years ago in the Stone Age, people were already observing the stars. They found patterns, and they did science in this way. You could think of this as early astronomy. We know that in Roman times, of course, first books were written on medicine. And in the medieval periods, especially in the Arabic world, all the groundwork was laid for algebra, lots of modern mathematics. That's where we have our numbers from. And indeed, even Newton, Kepler, and so on, they would cite a lot of this work by the medieval scholars. But if you look at Wikipedia or other sources, they will tell you, all right, but modern science, when did modern science start? And they always point back to Nicholas Copernicus, who, of course, changed our view from the sun is going around the earth to the earth is going around the sun. And again, I'm being very glib and cartoonishly simplified here, but a lot of people say that was such a big step and so much snowballed from that, that we can see that as a starting point of a scientific revolution. A lot of people say, well, that wasn't really the case when Copernicus came out. It had to go further. And in a way, it was because not so many people were aware of Copernicus until somebody came along who was a really good author. You could say he was a popular science writer. And that was Galileo Galilei. He wrote a book, and I'm not going to even try to pronounce the Italian. In English, it's called The Dialogue Concerning the Two Chief World Systems. And so what he does is he writes just really well. It's fun to read today. I brought the book for those of you that are interested. And so he has two people talk about these two worldviews, if the sun goes around the earth or the earth goes around the sun. And boy, did he get in trouble. So you can see this in the image right there, that he had to face the Roman Inquisition. He was eventually found vehemently suspect of heresy, and he was put under house arrest for the rest of his life. The book that I just held in my hands was put on the index of forbidden books and remained on there until 1835. And it wasn't until 1992 that a commission of the Vatican rehabilitated Galileo. And somebody had this idea that if you go to Italy, you can find Galileo's middle finger pointed and preserved. Any connection with that, I don't know. But some people say that Galileo, though, by writing this book, by starting what we think of modern science, he also might have made a mistake. What he insisted on is that science is mathematical. And he put it way more beautiful than I could ever do. This is a poor translation, but it gives you the gist. He said the book of nature is written in the language of mathematics. So he said that as scientists, we're trying to understand nature, and it's right in front of our eyes. It's the book of nature. But if you want to read it, you have to understand the language it's written in, and it's mathematics. Now, this was taken a step further a little bit later by his colleague René Descartes. Descartes has many, many important ideas to his name. Probably the most important is in mathematics. He was the first who came up with what we now call the Cartesian coordinate system. That doesn't seem such a big deal to us. But you have to think about that up until this point, mathematics was taught as geometry and algebra, two completely separate branches. This combines the two. So he was definitely an important person. And he was aware of what happened with Galileo and the Inquisition. He wrote very important books. The one that I'm highlighting here is the Meditations on First Philosophy, in which the existence of God and the immortality of the soul are demonstrated. So you can already see that Galileo clashed with faith of the time. Descartes seems to lean on the other side. He also was aware and criticized that Galileo made a mistake when it came to explaining the tides of the Earth. And he was correct, Descartes was, with his criticism. And his whole take, whether that was influenced by the fact that Galileo ran in trouble or not, but his whole take was that reason and faith should be reconcilable. And he made a very important step in that. He came up with this idea that we now call Cartesian, after his name, dualism, where he's saying the world is physical, all right. That's the domain of physics. And then there's the mental. Now we would say psychology. But he created a divide. They said those are completely separate worlds, separate realms. And you can see that in a way maybe as handing over the peace pipe or creating a truce by saying that we'll just deal with one of these worlds, the physical world, and we're leaving the spiritual, the mental world, to other things. And so I believe that even though he was never very explicit in that, that is what underlies a lot of scientific thought, this fundamental dualism. And it is appealing because it makes sense. He said, just think about it. Anything that's made out of matter takes up space. But if I think about your mind or the color red, it seems spaceless. So there are fundamentally different attributes to the mental and the physical, hence they must be two different things. And that thought has prevailed until the modern day. And of course, Cartesian dualism was never banned, just like Galileo. And for some weird coincidence, the remains of René Descartes lack a middle finger, and it is, or a finger, I should say, and we do not even know where it is. So I'm not the only person who has thought about these things. I'm not the only person who believes that when it comes to science's troubles with consciousness, we have to go all the way back to that point. Otherwise, I wouldn't have bothered to tell you. Some people made a mistake with Galileo's insistence on mathematics. People like me would rather lean towards the Cartesian view of creating this gap between the physical and consciousness. Either way, we started off on the wrong foot. We immediately defined consciousness as something that is off limits to science. So in other words, we say there's the book of nature that's written in mathematics. And then on the other side, and here are some quotes that I'm being a little bit unfair to these authors because they're not scientists, but you can find that online nonetheless. You can't measure love, or you cannot measure love by a scale of degrees. So you're having on the one hand side things that are mathematical, there's laws of nature, and on the other side you have the immaterial, the immeasurable, the unquantifiable, the non-mathematical. To make it even more simple, what this looks like is we have things that mathematics describes, and it's vast. Of course, there are things outside of science that are still within math, but everything that we think of natural sciences in the end turns into equation, laws of nature, mathematics, when consciousness is out there. immaterial, inquantifiable, and so on. That was the case until the 1800s. And then this guy came along, Gustav Fechner. And he was a little bit of an eccentric. He never managed to get tenure and get a lifelong career. He wrote some really bizarre books. But he did something very important. He found out that when it comes to your subjective perception, it can be rigorously measured, it can be precisely quantified, and it follows mathematical laws. Everything that I just said that beforehand we thought should be separated isn't anymore. And so you might have heard about this. This was the father or inventor of psychophysics. And what he found is, and I showed this demo here to the left, if you look at 10 dots versus 20 dots, for example, you can clearly see that there's more dots below in the 20 dots example. There's 10 dots more, but you can see it, okay? But if you look at 110 dots and 120 dots, it's very difficult to see that there's 10 dots more. So this is just one example where he realized that, and you can see in the middle right there, we can measure these things by asking you these questions, being very precise, doing very precise experiments. And then when we do these experiments, we find laws of nature. We find equations, we find curves, everything that we find elsewhere. And hence, there was this name of psychophysics. So what Fechner did, I argue, is that when it comes to the separation of consciousness from the rest of the physical world, because it's amathematical, he did this. Now consciousness falls squarely into the mathematically described, and therefore into what science wants to do. Now then there was a hiccup. So soon after all of this triumph of psychophysics, we had Sigmund Freud and other people come along and almost suck all of the rigor out of psychology. That was noticed by philosophers. It wasn't just psychology, but there was a notice that we lost rigor in the sciences, and Karl Popper is often mentioned when it comes to that. And there was an attempt to rescue science and make it rigorous again. And they overdid it, I argue. So what happened next is in psychology what we call behaviorism. And that was a good move. We made a lot of progress by becoming behaviorists and just studying behavior. But of course, it limits you to studying behavior. If you're interested in consciousness, you eliminated it. You will not be able to study this anymore. Now this changed thanks to the efforts of a lot of great minds. And I'm just pointing out a few here. There's too many to list. But I think if there would be a survey, a lot of people would point out some of these names. I'm showing you Christoph Koch and Francis Crick here. Francis Crick might be familiar to you as one of the two authors of the famous paper that describes the double helix structure of the DNA. Got the Nobel Prize. Went on to decipher most of the genetic code to get the triplets that translate from RNA to amino acids. And spent the later years of his life on working on consciousness. And it helped to have somebody that well established, obviously a great scientist, to say this is scientific. And what they did back then is to say we can do neuroscience of consciousness. In particular, what we can do is we can look for correlates. We can look for neural processes, things that go on in your brain that have something to do with consciousness. And again, I went to PubMed, and if you put this in, you can see that there has been some explosion of activity ever since. So what was this research program? This research program was to find neural activity that co-varies with certain conscious content. That implies, of course, that there is neural activity that you have that doesn't. And there's plenty. So you probably have heard that you have a lot of nervous cells around your gut, like a little brain around your intestines, but you're not conscious of it. You can remove the entire cerebellum, and you're still pretty much the same person. You might have some Parkinson's-like symptoms, but it doesn't seem to affect your consciousness, even though there are more neurons in the cerebellum than the rest of your brain. So there seems to be something inside your brain that co-varies or correlates with consciousness, and then a whole lot of stuff that has nothing to do with your subjective experience. And the idea is to find that. And this was done in many, many, many studies. I'm just going to point out one of the results here by Itzhak Fried, a neurosurgeon at UCLA, and Rafi Malach, who's at the Weizmann Institute. And they had a great paper, and we'll see if this movie works. You can hear the neuron crackling. You can see some scenes that a patient is looking at. And it looks like this neuron didn't respond to anything in the brain of this person except the Simpsons. And if you show basketball again, this neuron stops responding. So the interesting question here was, is this a neuron that has something to do with the Simpsons? So they asked the patient to recall, what did you just see? What were these various scenes that you were just looking at? Jump here. Something about New York, no response. Hollywood sign, no response. And you see it coming. Watch what happens first. The neuron starts responding. Supposedly, there's something going on in the consciousness of the Simpsons, and the person says the Simpsons. That is what we would call a neural correlate of consciousness. Of course, you have to do more controls than what I just showed you. But it shows you that we can do this. We can put electrodes in brains of people, animals, and so on, be very precise, rigorous, do these tests, and we find neurons that seem to have a privileged access, some kind of relationship to the conscious content. What they do might be part of what is giving you conscious content. You can think of these as mind reader neurons. If we find these neurons, we could find out what's in your consciousness, but we found these neurons. That was great success in the late 90s or so. It's been a while. Now, of course, the inverse would be more satisfying. You might want to say, I am not satisfied with correlations, covariations. Show me the causal relations. OK, so the next step would be to show that there's causal relations. And again, there's a lot of work. I'm just going to point on one. This is José Manuel Rodriguez Delgado. And he got famous a long time ago. That's why this is a black and white photograph, by putting electrodes in the brain, in this case of a steer, and then provoking the steer while having a remote control in his hand. And right at the moment before he would get killed, he would push the button, and there would be current remotely flowing into the brain of the steer, and the steer would freeze. So if you put electrodes in the caudate nucleus of a bull, you can get it to stop charging at you. And so that would be at least proof that we can change the behavior by influencing the brain. What about perception? So let me show you this video, which I borrow from my colleague Kalanit Spector. It's a patient who has electrodes in the brain. You can't see them. This has to be done for certain types of epilepsy to treat these people. And they use this to stimulate just a little bit, just with the ball, the brain of this person. But it's a different part. It's the visual part. So let's see what happens to this patient.
Just look at my face and tell me what happens when I do this, all right?
So at first they run a sham.
1, 2, 3.
It's a control. Nothing should happen.
Nothing?
Nothing.
Okay.
Now they will do it again, and they will run current.
Look at my face. 1, 2, 3.
You just turned into somebody else.
Tell me
Your
about
face metamorphosed.
So that is not surprising, given what some of you have probably learned about the visual system. There's part of your visual system that is especially interested in faces, a response to faces. If you run currents to it, it distorts the faces that you see. So we have not just only, obviously, there's hundreds of papers, OK? So I'm just giving you a feel for it. So we found neural activity that co-varies with consciousness, or conscious content, I should be more precise, and neural activity that causally influences or even determines the conscious content. That's ongoing work. It's very interesting, but you have to ask yourself, if you're not an engineer who's interested in, let's say, work with Elon Musk on doing exactly that we can have a VR world eventually, where we don't have to wear goggles, we just directly stimulate the visual cortex, or we can read out what people think. That is engineering, that's not science. It doesn't tell us how this works. So what else can we do? And so in fact, I would argue this whole research line has slowed down because of that problem. It's unclear where this is headed. It's interesting, all right? But as scientists, it seems that we want more. And I want to talk about this more. So in the beginning of the talk, I gave a hint at what I mean by that. So here's another quote by Johannes Kepler, one of these influential astronomers when it came to a rethinking of the solar system. And so he says it very clearly. The chief aim of all investigations of the external world should be to discover the rational order and harmony revealed to us in the language of mathematics. And of course, if we go to the core of science, physics, that's all we find. These are a handful of equations that I pulled out that physicists might or might not agree with me, explain everything from the smallest that we know exists, the Planck unit at 10 to the minus 35 meters, to the largest that we think exists. That's, of course, an approximation. But the largest that people think, and I took the largest, would be 28 billion parsecs. That would be 93 billion light years, accounting for the inflationary period right after the Big Bang. That's how big the universe is finite at this point, if you believe the Big Bang theory. And the universe is not infinitely small either, if you believe quantum physics. There's a minimum and a maximum. I'm putting it out there, and we believe that we can explain everything in between with these equations. Identities. All that we do there is we say, this is this. And those statements allow us to make sense of the physical world, put a man on the moon, build MRI machines, laser pointers, and iPhones. So there's power in mathematics, and it might be the end point of everything that we want to do. Maurice Klein, who was a mathematician, and I'm kind of boring his words, he said the goal of scientific activity should be quantitative mathematical laws. That should be the end goal. Maybe it shouldn't be the end goal, but it sure looks like it. Once we have that, it seems discussion ceases. We have very little discussion about the Schrödinger equation. There seems to be something about mathematics that seems to be closer to what really is, maybe, that we're satisfied when we reach this level of description. Now, why that is the case, that is something I leave you to have sleepless nights over. So Einstein put it very poetically by saying, how is it possible that mathematics, a product of human thought that is independent of experience, fits so excellently the objects of physical reality? Eugene Wigner, a fellow Tennessean who worked at Oak Ridge, helped build the nuclear bomb, he said, we don't deserve this. It's inexplicable how we can understand mathematics, and it seems to so exquisitely, so efficiently explain what we find in science. And to just give you an idea of what this means, Neptune was predicted to exist long before we knew it did, because we had the equations, and the equations told us there has to be another planet. The Higgs boson was predicted decades before we just found it a couple of years ago, because of the mathematics. It's the other way around. It's not us observing and then coming up with equations. We're often at this point that the equations tell us what to observe, and then we look and we find it. That is very convincing, that there's power to mathematics. Now, when it comes to consciousness, I told you that we were so focused on observing, on finding correlates, causal mechanisms, that what happened in the last couple of years is revolutionary. There's been an influx of mathematicians, physicists, and a concerted effort, and I'm just putting out some YouTube channels here that I think are interesting to watch or part of this wave, some conferences, some very generous foundations, institutions that help fund this. And so there's now not only an empirical, observational, experimental neuroscience of consciousness, but there's also inroads into the theory, the mathematics that might lie behind that. And if you indulge me for a couple more minutes, I want to give you a little bit of an overview what I mean by that. To summarize, and this often gets lost, what this could lead to, what is the endpoint of that? I'm taking a quote here of my friend and colleague Johannes Kleiner, who wrote in 2020 that the central idea of this research program is to represent phenomenal consciousness. So again, that is your subjective experience, no more, no less, in terms of mathematical spaces that then can be related to the physical domain. In words, that doesn't mean probably much, but you are already acquainted to that. So when it comes to the perception of color, for example, when you learn about color in vision, you will immediately confront geometry. The way that we understand color is as a location on a three-dimensional sphere. Every color has a street address within or on that three-dimensional sphere. So that is what we mean by structure. It's geometry. It means relations between, in this case, all of the different colors. If you take all the relation that you have with all the people in the world, your Facebook connections, Instagram, we could do something similar. We could create a space where there are connections, relations between you and everybody else, and we just do this here for color, same thing. We don't do that just for color. We also do that for music. This is the geometry of music, or a very simplified attempt at that. So what we mean by that is that if you go higher in notes in music, you go higher, and you can see this by this vertical elevation. But there's this bizarre thing that happens in music that when you go exactly a certain number of steps higher, 1 octave, you find the same note. So instead of just jumping up vertically, it seems like we loop around in a helix. And so we end up, in some sense, at the same location again. So if you listen to a song, or I double the frequency of every note that you heard. It's completely different physics. What happens is that you just jump up in the helix. Same song, 1 octave higher. You recognize it as the same song, it's just shifted a little bit up in the helix. So this strange property that you're going higher and yet it's similar, we can geometrically capture, in this case by a helix. Sorry about that. Lastly, and that's just another example, when it comes to phase perception, for example, people have found the exact same thing applies. So here's a previous supervisor of mine, David Leopold, and he did astonishing work, beautiful work, behavioral work, and also neural work, that points to the fact that there's a geometric space of faces, with the average face of all the faces that you've ever seen lying at the center, and every face being a vector that deviates from the average face. There's many implications that might immediately shoot through your mind. If that's true, we could test this and this and this, and that's exactly what David did, and so far it holds. But all I want to say is that it is not bizarre to think of your consciousness and your conscious content as geometry, as structures, as mathematics, or as something that can be mathematically described. And I don't think I have to make the case that that's true for the physical world. Now, there's many theories that coexist, I should say, that have made inroads into what consciousness is, how it relates to the brain and neuroscience. I'm just highlighting two: integrated information theory and the free energy principle, since they are, or they contain, I should rather say, mathematical equations. They contain mathematical formalization. There's more theories. Most of them still await mathematical formalization, and people are working on it, and I can't wait until the day that is. Now, for the remainder of the talk, I will focus on one of them, integrated information theory, but that doesn't necessarily mean endorsement or that I'm married to it. I just want to give you an idea. I certainly see certain merits, and we can discuss about it more later on. So ideally, of course, you would have one equation, or at least some kind of mapping where the brain and the brain activity is on the left-hand side, and then some mathematical operation, and then we have consciousness on the right-hand side. We're not at this point yet that there's one equation. So integrated information theory, and in fact it's a simplified version, has that many equations. It looks more difficult than it is. And I'm not going to walk you through all of the mathematics of integrated information theory. If you are interested, there's a 20-minute video on my YouTube channel where I go about half the way of all of this, and it can give you a pretty good intuition. But what I want to emphasize is that this, whether it's true or not, whether people like it or not, is a step forward. And I'm not going to make this case by myself. I'm going to borrow words again, in this case, from John Bell. John Bell was a physicist who should have gotten a Nobel Prize last year. He didn't, because he passed away. So people got the Nobel Prize for doing experiments proving John Bell right. Now, I will not talk about quantum physics today and what John Bell did. I'm just steal some of his words. So this is what John Bell said at some point. He said, this theory may not be beautiful. It may not be true either, although it might give some hint on where truth is to be found. I do think, however, that it has a certain kind of goodness, in the sense that it is an honest attempt at replacing woolly words with real mathematical equations, equations which you do not have to talk away, equations which you simply calculate with and take the results seriously. So I think what he's saying here is that whenever we are able to replace imprecise terms that we use in our language, that I'm doing right now, that can lead to misunderstanding, to debate, to different people talking past each other, and we can condense it down to the formalism of mathematics, we have made progress because we understand each other better now at this point. That is what he means by woolly words. The debates, the controversies, can be more focused on the actual issue and less about people meaning different things with the same words. That is why I think this is progress. The next one is that once we have mathematics, we can be quantitative. That means we can calculate, we can compute. And so what that means is that when it comes to science, this is one of the principles that people often point out, is we should test the consequences of our assumptions rather than the assumptions themselves. Let me soften that, relax it. If you struggle to test an assumption that you have, you can still test the consequences to see if this assumption has merit or not. And just give me, borrowing from physics again, give you an example. The Big Bang Theory is a big assumption that many of us share, but we cannot observe the Big Bang. It's beyond a horizon that lets us observe. We cannot test it. We cannot repeat it in the laboratory. Yet we think it's science. What we can do is we can test predictions or consequences of that assumption. For example, that there's anisotropy in a microwave background radiation, and as you might be familiar with, we find that. Now, it should also be noted that this doesn't mean that the Big Bang Theory is true. No serious scientist would ever say something as foolish. It just means that there's many alternatives to that idea that seem less likely. They struggle to explain some of the things that we observe that make more sense under the Big Bang Theory. Now, the Big Bang Theory has run into trouble itself. Not everything we observe makes sense in a simple Big Bang Theory. Those of you that are tuned into other parts of science, you might be very well aware that we are running into a so-called crisis in cosmology, where there's more and more evidence, as we're measuring things more precisely, that embarrass the Big Bang Theory. And so far, the approach has been what some would call a Band-Aid. So sometimes we just modify the theory so that it accounts for the new incoming evidence. So Lakatos, who's one of the great philosophers of science, he said that that is how science really progresses. We're not just throwing out a theory if there's a problem, we're patching it. And then once it is all over Band-Aids, it's probably time to abandon the theory and then we move on. That is when we get an actual paradigm shift. So that's not the case yet for the Big Bang Theory, but it can happen. Nobody can predict the future. So that means future scientists may not believe in the Big Bang Theory, and that's all right. They will not blame us for having done something foolish. At every point in time, we have to come up with the best explanations given the data that we have at that point. And in the Big Bang Theory, many other theories of physics, we're not testing the theory itself. We are testing predictions or assumptions that are derived from the theory. And so that is true for integrated information theory. That's the last part I'm going to show you, just give you an idea. So one of the predictions of integrated information theory is that the brain integrates information, put it more simply. So a very clever experiment that has been devised is called Zap and Zip. It's called Zap and Zip because you zap the brain with TMS. So it's a very strong electromagnetic pulse, and it causes your brain, all of these neurons, to fire pretty much at the same time. And you can measure the outcome of that with the electroencephalogram, with EEG. So you put electrodes all over the brain, you can see the voltages that are evoked by brain activity, and then you disrupt it with this pulse, and you see what happens. So these are experiments that can be very easily done, they're not painful, you get them approved by the IRB and ethics committees. This is somebody who's volunteering. You can see the EEG electrodes, you can see the TMS coil, and so you can do things, for example, have people be conscious, just be awake, do it, see what happens. Integrated information theory would say, you should see some form of integration. And then you can have people fall asleep into deep sleep, where most of us would probably agree it seems like where there's no consciousness. You seem to cease to exist, or the world seems to cease to exist for you. There's like a cut in the movie that's your life. People can look at you, you're still there, but You do not dream. You do not have this experience that you have right now. So it seems like your brain is in a different mode. There's no consciousness. And so the theory would say there's no integrated formation. And so, of course, you can do anesthesia, you can do coma, you can do all of these things, and people have done it. This were the first experiments where my ears perked up. And I said, this theory, years ago, predicted these findings. They looked, and that's what they find. To the left-hand side, you see wakefulness. You see a stroke patient. You see REM sleep, which is the dream-like sleep where you are conscious. And you see ketamine. Ketamine is an interesting drug. Ketamine, a lot of people think, is not an anesthetic that knocks you unconscious. Ketamine puts you in what some people call a dissociated state or disconnected state, where you are fully conscious, but people can chop off an arm and you would not respond. That is because your brain is dreaming. It's not responding anymore to the outside world. It's a dangerous drug because people do chop off their arms while they're on ketamine. Propofol, non-REM sleep, midazolam, and xenon, these are all various anesthetics that some of you might have been unfortunate enough to be exposed to in your lives. Of course, non-REM sleep, most of us did last night. And you can see the difference. So you can see the vertical pulse, and you can see there's more squiggly lines. There's more going on when these people are conscious, including REM sleep. They're sleeping. And you see that there's almost nothing, no integration, people would say, in the unconscious state. And there's many, this is actually just a selection of studies that I'm showing you. It has been shown many times. Why is this important? Well, there are people who undergo extreme traumatic brain injury, and they end up in the emergency room, and decisions have to be made whether these people are conscious or not. And there are ways that clinicians have come up with, but fundamentally they face this problem. You're just looking at a person. So if you're poking a person with a needle and it doesn't respond, is that person comatose, or did it lose all will to act? Is that person so depressed that they wouldn't even respond to that? Or maybe the motor cortex is destroyed. These people feel the pain but cannot respond. Maybe it's locked-in syndrome, where the whole muscle system is not under control of the central nervous system anymore. Just looking at behavior, you just won't be able to do the difference. And in fact, we found comatose patients over the last decade or so, where it seems that they are conscious, they just cannot communicate. That was done with fMRI. You could put them in an fMRI machine. You can talk to them and say, if you're conscious, imagine walking through your house. Or if you're conscious, imagine a face. And then you see activity in the face area or the place area. This right here, there's no fMRI machine in the emergency room, of course. This right here, though, works. So I'm going to show you a brief video that I have from my friend and colleague, Marcello Massimini. And you can see a patient undergoing this procedure. So this is, as you can see, a patient that is about to be diagnosed as comatose or not. You can see the EEG, you can see the TMS, and you can see the clinicians working here. I forget the name of the attending neurologist. They're just running this experiment. This patient is non-communicative. And you can immediately see the results right there. So they actually founded a company that they hope will allow this technique to be used more in the future. And if you watch Marcello's talk, Marcello Massimini, easy to find on YouTube, he will show you examples of patients where the clinicians thought this patient is in vegetative state, non-rescuable coma. This technique said no, so they kept trying. And a day or two later, they were able to communicate with the patient. The patient was able to move a finger because they thought maybe it is not a disorder of consciousness, maybe it's a movement disorder. They gave basically drugs against Parkinson's, changed the dopamine system, and the patient was able to move a finger and indicate, I want to go to rehab. So everything that I told you about so far is not just theory, is not just people that are curious and interesting. It is actually part of our societal responsibility to answer some of these questions in terms of, if you look at a brain, do you know whether somebody's there, whether the lights are on or off? And though all of these other questions, of course, memory, all these functions are equally important, it might be a mistake to, especially right off the get-go, exclude consciousness from this line of research. I'm just going to briefly mention that this theory, integrated information theory, is working on the next steps, because that is a question that often arises. if this theory, if these mathematics explain consciousness, then explain to me why sound sounds like sound and seeing is like seeing. And that is exactly what they do. So you can derive the properties of vision out of the mathematics of integrated information theory. You can derive the property of why time feels like time from the properties of integrated information theory. So it's a huge research program, but it is a lot of effort, and it's not without flaws and problems. So I'm just going to list a whole bunch of problems that people have pointed out that I have with integrated information theory, again showing you that nothing is perfect. We should see this as a step forward, that this and other theories have taken a mathematical term. They're formalizing things. They're allowing us to be precise. They're allowing us to be rigorous. They're allowing us to calculate. They're allowing us to put brain data in and see what comes out. But that doesn't mean that they're correct or beautiful, but they're good because they allow us to take that step forward. And more precisely, when it comes to IIT itself, you can think of it as a theory consisting of many, many different modules of mathematics. I'm just plotting some of them here. Each of them has either existed before or is newly combined with other things, or some of them actually are newly derived because of interest in integrated information theory. That means if the theory is thought through, we have to change certain things in mathematics. So the way that we think of information, for example, Shannon information, the classic tool of computer science, it is not exactly useful in integrated information theory. So if you're familiar with Shannon information, you can see this equation looks very familiar, yet it's slightly different. So we had to change some of the mathematics, and I will argue that at the very least, there's merit in this theory that we can take some of these mathematical modules and we can study those. You do not have to accept or buy the whole theory. But the mere fact that we have mathematization allows for progress. So, long story short, I believe that when it comes to science, we are all scientists. We like and appreciate this, that you can take observations, physics, matter, and you can be rigorous using mathematics. You can make sense of what happens, in this case, Einstein's equation. And it seemed for the longest time, at least when I was a graduate student, when I started, that the reason to enter this field is that we're not there yet. Instead, we were at this point. We knew brain leads to consciousness, but if you would ask people, they would be embarrassed and would have to wave their hands and say emergence or something that doesn't really explain what is happening. And the mathematical turn in the last 5 years or so is now shifting us over into what seems more explicable and readily accessible and acceptable to most of us scientists. And with that, thank you very much.